Okay, today we are going to learn how to calculate equilibrium constants. We've learned how to write the expression for equilibrium constants. Now we're going to learn how to calculate the value, the numerical value, or the numerical magnitude, that just means how big it is, of K. Okay, so here we have a sample problem. We want to calculate K, our equilibrium constant, when we know all equilibrium concentrations. After a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium, so it's at equilibrium, at 472 Celsius at a temperature, it is found to contain 7.38 atmospheres of hydrogen, 2.46 atmospheres of nitrogen, and 0.166 atmospheres of ammonia gas. From these data, calculate the equilibrium constant K, P for the reaction. N2 plus 3H2 makes 2 ammonias. This is the Haber-Bosch process. So the first thing we need to do is write the equilibrium expression. Kp is going to be equal to the concentration of our ammonia to the second power, because of this 2, divided by the concentration of our reactants. We have N2, and these are gases, so we include them, and that's to the first power, times H2 to the third power because of this 3. Now, to figure out the value of Kp, we will substitute numbers in for each of these symbols. So let's do that. We know that our NH3, let's find it here, is 0.166 atmospheres. So 0.166, that's going to be to the second power because of this 2 here. Okay, let's use a different color. So our N2 here is 2.46 atmospheres. So for N2, I'm going to put in 2.46, and that is to the first power. And our H2, 7.38 atmospheres, and that is to the third power. Okay, so I calculate a 0.166 squared is 0.027556. We have 2.46 down here, that's to the first power, and 7.38 cubed is 401.95. I went ahead and wrote in atmospheres for each of these, only because it's important that even though K is unitless, it's important that all these units be the same, otherwise we'd have to convert. So when we then take this expression and square this, I did square that. We will divide this, don't like that color. So if we divide this by this times this, we come up with a Kp that is 2.787. Really, I should make this 2.79, 3 significant figures, times 10 to the negative 5th. That is the value of our equilibrium constant that we found by substitution. Okay, we will now work another problem. You can work this and then check your work, or you can follow along with me. So an aqueous solution of acetic acid is found to have the following equilibrium concentrations at 25 degrees Celsius. So this means it is at equilibrium. Here are our concentrations. Calculate the equilibrium constant Kc for the ionization of acetic acid at 25 degrees Celsius. And this is the reaction for the ionization of acetic acid. And by ionization, they mean it splits into ions. We'll talk about this in our next unit. So the first thing we will do is write the expression for the equilibrium constant. So I have written the expression for the equilibrium constant. We have our 2 products in the numerator, our reactant in the denominator. These are all aqueous, so they have concentrations, so we include them. Now, to find the value of this equilibrium constant, we will substitute and solve. So I'm going to take these numbers and put them in for these concentrations. So the value for the hydrogen ion concentration is up here. I'm going to put that here. 5.44 times 10 to the minus fourth, and these brackets mean molarity, and this is molarity. So the concentration of the acetate ion here, I'm going to put here, that is 5.44 times 10 to the minus fourth also. And at equilibrium, the concentration of acetic acid is up here, and that is 1.65 times 10 to the minus 2 molar. Now I will multiply this times this and divide by this to simplify. So if I multiply 5.44 times 5.44, I get 29.594. 10 to the minus fourth squared is times 10 to the minus eighth. That now is divided by this. 29.594 divided by 1.65, 17.935. 10 to the minus eighth divided by 10 to the minus 2 is 10 to the minus 8 plus 2. You get 10 to the minus 6. And we can simplify this isn't correct scientific notation, into 1.79 times 10 to the minus 5. And I use 3 significant figures because I have 3 significant figures here. So this is the value of the equilibrium constant given these equilibrium concentrations. So that is how you substitute and solve when you know the concentrations at equilibrium. In the next tutorial, we will talk about what to do when you only know initial concentrations.